groundwater and soil remediation. A little bit about me. Those of you who have not had a webinar with me, as Jerry mentioned, I'm a Massachusetts licensed hazardous waste site cleanup professional, licensed site professional, or LSP for short. I am also a certified professional geologist through the American Institute of Professional Geology and a professional geologist licensed in New Hampshire. My other job, I'm an adjunct professor of geology, both at Bridgewater State University, Northeastern University, and Wentworth Institute of Technology. I have a bachelor's and a master's degree in geology, and I've been working as an environmental consultant for over 37 years with a variety of firms. Right now, I have my own sole practitioner consulting practice, Penzo Consulting. So I've been a licensed site professional for 20 years, and I have been an environmental consultant for, again, over 37 years. So our agenda today, we're going to talk about contaminants of concern. Before you can clean up soil and groundwater, you have to know what you're cleaning up. So we'll talk about volatile organic compounds, semi-volatile organic compounds, metals, PCBs and pesticides, and some emerging contaminants that I'm actually doing a couple of projects on right now. We'll talk about groundwater remediation methods. Some are older than others. The good old groundwater pump and treat, along with dual phase pump and treat. I'll talk about capture zones and hydrodynamic isolation, the treatment of dissolved volatile organic compounds, as well as other compounds, the recovery of non-aqueous phase liquids, both light and dense non-aqueous phase liquids, remediation by using reactive walls, using soil vapor extraction, kind of a variation on soil vapor extraction is air sparging and bioslurping, and also bioremediation. Under soil remediation, we'll talk about excavation, kind of the old school standard underground storage tank excavation and removal and soil removal. Some in situ treatment technologies, ex situ treatment, off-site disposal. And then we'll talk briefly about soil bioremediation, encapsulation, and containment. Groundwater and soil remediation are regulated federally under RCRA and CERCLA, and under the state in Massachusetts under the regulations called the Massachusetts Contingency Plan, which is similar to the national contingency plan the federal government has. And we'll talk a little bit about some programs in other states. So, since the early 1980s, groundwater scientists and engineers have developed a number of techniques for containing and remediation of soil and groundwater contamination. In the U.S., this has been driven by the Resource Conservation and Recovery Act, RCRA, and the Comprehensive Environmental Response, Compensation, and Liability Act, CERCLA, or Superfund. It's a mouthful. In Massachusetts, this has been driven by Massachusetts General Law, Chapter 21E, and the Massachusetts Contingency Plan, 310 CMR, which is the Code of Massachusetts Regulations 40.000. Other states have their own specific laws and regulations related to the assessment and remediation of contaminated sites. Massachusetts is a little bit different because we have a privatized program, and I'll talk about that a little bit later. So our learning objectives. Well, the purpose of the course is to provide you with some specific knowledge and skills about groundwater and soil remediation technologies, a little bit about both RCRA and CERCLA, Superfund, and I'll concentrate mostly on the Massachusetts regulations. So when we talk about contaminants of concern, we talk about various categories. The one that I have done probably most of my remediation work is in dealing with volatile organic compounds. Some examples, benzene, and you see in the upper right-hand corner, the benzene ring, and a lot of other contaminants, aromatic contaminants, have one or more benzene rings attached. Ethylbenzene, toluene, xylenes, and those are related to the light-end petroleum compounds, additives, but also I've dealt extensichloride with chlorinated solvents related to dry cleaning fluids and degreasing fluids, and tetrachloroethylene, also known as PCE, trichloroethylene, TCE, 1,1,1 trichloroethane, vinyl chloride, and kind of thrown in this is dioxin. Semi-volatile organic compounds, naphthalene, benzoate-pyrene, phenanthrene, anthracene. Many of these VOCs and semi-VOCs are also, in addition to being toxic, they are also carcinogenic, cancer-causing. Metals, kind of four of the primary metals of concern: lead, cadmium, chromium, and mercury. Lead, you've all heard about what's going on in Flint, Michigan, their lead contamination in water. But in addition to water contamination, soil contamination is a real issue. Paint chips are an issue. Lead can cause developmental delay. It can cause emotional issues, emotional dysregulation. It can cause other neurological problems. Mercury, excuse me, mercury as a metal is not particularly toxic, but when it biodegrades to methylmercury, that is soluble in water, and you've probably been told, I don't know where you are, but if you've eaten a lot of seafood or sushi, you've been told to try to restrict your consumption of things like swordfish and tuna because it has bioaccumulated mercury in it, and eating too much is not good for you. So, other contaminants, PCBs, polychlorinated biphenyls, used extensively as a transformer fluid, and those are broken down into aerochlors and congeners. Those also bioaccumulate and can cause some severe health problems. Pesticides, things like DDT, aldrin, dieldrin, endrin, these four are banned in the U.S. DDT in particular, if you ever read Rachel Carson's book, The Silent Spring, it talks about how DDT is also bioaccumulative and can cause, it acts as an environmental hormone in your body. It almost wiped out the bald eagles in the United States. Others, acids and bases, you know, if you your skin comes in contact with an acid with a low pH or a base with a very high pH, that it's going to cause you problems. And then some emerging contaminants that I've dealt with, 1,4-dioxane, which is found in various products. Also, it's found in munitions. PFAS, which is polyfluorinated compounds. These are really common. We find them in firefighting foam, the wax paper on your pizza boxes. If you ever bought a raincoat that has Gore-Tex in it, well, the old formula Gore-Tex was PFAS and Teflon. So you can't help but be exposed to it. And the issue with it is it has health effects in extremely low concentrations. Most of the cleanup standards for most of these other compounds we've talked about, we're dealing in either parts per million or parts per billion. Well, when we get down to PFAS before, we're talking about parts per trillion or nanograms per liter, nanograms per kilogram. Some of the others that we don't think of as being contaminants, but they are: pharmaceuticals, hormones, antibiotics, and personal care products. So we have all these contaminants in the environment. How do we clean them up? Well, the groundwater remediation methods we'll talk about are pump and treat, hydrodynamic isolation. Once you've pumped it and treated it, how do you get rid of the treated groundwater? Well, you either discharge it or recharge it. We'll talk about dual phase pump and treat, how we treat dissolved VOCs, among other things, the recovery of NAPLs, and then, as I mentioned, reactive walls, soil vapor extraction, air sparging, and bioslurping, and bioremediation. So, pump and treat, a very common technology. Basically, it is the same technology we use to pump our groundwater for our drinking water wells. The process is to pump groundwater, pump it enough to contain the area of dissolved contamination in groundwater and remove it. When the groundwater gets extracted, it's treated by a variety of methods and then either re-injected into the aquifer or discharged to the surface water or perhaps to a sanitary sewer. And you can see that here's the groundwater, the dissolved plume. When you pump groundwater, you will depress the water table, and this is called a cone of depression. You see a little cone shape. The groundwater is flowing this direction, so the extraction well is hydraulically down gradient from the source and from the dissolved plume. So it's pumped, it's treated, and then it's discharged. When I talk about hydrodynamic isolation, we can control the pumping rates of these extraction wells or multiple extraction wells, and this can be used to isolate a zone where the groundwater has been contaminated. An extraction well at the leading edge of a contaminant plume can be used to stabilize the position of the plume. And we calculate the capture zone of the pumping well, and we do that by performing computer models, but in the field, we're performing aquifer pumping tests using the drawdown in the pumping well, but also looking at the drawdown in surrounding monitoring wells. The treated water can be discharged to a receiving water body under a National Pollution Discharge and Elimination System and called NPDES permit, or it can be recharged to the aquifer with an injection well, which may be regulated under the Underground Injection and Control Program, UIC, or it can be discharged, or actually recharged back into the aquifer using a leaching system, a leaching field, not unlike a septic system leaching field. So the groundwater that contains these dissolved contaminants can be removed from the groundwater by this pumping and treatment method. The advantage is that it can use conventional methods of wastewater treatment, or it could use specialized type of treatment. If there are non-aqueous phase liquids present, now you'll hear me use the term now, that's what I'm talking about. Think of pure chlorinated solvents, pure oil, pure gasoline. And there are two ways to handle these types of free phase liquids. Either you pump the fluid out of the ground together, pump everything out by using pump and treat, and then separated above ground, and the water being treated and the NAPL get properly disposed of, or in some cases it can be recycled. Or use a dual pump system, pumping each fluid out separately, and the pump and treat systems are not as frequently used as in the past due to newer technologies. The thing about groundwater pumping and treating, and I've put in probably about 100 of these types of systems, is once you turn it on, it's very difficult to turn it off, because while you can do a fairly good job treating the dissolved contamination, getting NAPL out of an aquifer is extremely difficult. There are new regulations and new types of scientific studies that talk about mobile versus non-mobile NAPLs in the environment. And Massachusetts has changed their regs to take that into account. So another method is dual phase pump and treat. And the two phases we're talking about are not water and NAPL. We're talking about water and soil vapor. In this case, it combines the technologies of groundwater pump and treat and soil vapor extraction together in one well. And the groundwater is extracted through a conventional water pump, and that water is brought above ground. It goes through a treatment system and discharged. At the same time, it's depressing the water table. And you see that in the area of this pumping well, the water table has been depressed. And this isn't to scale, but this could be up to 10 or 12 feet. This creates, and the well screen, in fact, is throughout this entire, from the bottom up to about this point. The well screen, the slided well screen, or wire-wrapped well screen, allows water in to be pumped out. But once you lower the water table, it will allow soil vapor to enter. And instead of being pumped by a water pump, it is being drawn by vacuum extraction. So the vacuum flow draws the soil gas, which has a certain amount of water in it. Vacuum flow goes up, goes to a gas or vapor water separator, also called a knockout pot. So the water is separated out, and that water would be also eventually discharged or treated and discharged. The soil vapor, which still has a fair amount of volatile organics in it, is pulled with a vacuum blower, and then eventually it goes to a vapor phase treatment system. And typically this is going to be vapor phase granular activated carbon. We'll talk about it in a few minutes. Or it would be, it could go through catalytic incineration. So there are a few methods, a few common methods anyway, of treating dissolved volatile organic compounds, among other things. Granular activated carbon, tray aeration air stripping and air stripping towers, catalytic incineration, ultraviolet oxidation, and ozone water purification. In terms of granular activated carbon filtration, so don't think of like charcoal, like a charcoal briquette like you use to barbecue. What we're dealing with is, this is basically, they make charcoal, and typically they use coconut shells. It's got a lot of pore space in it. They burn it into charcoal. Then they treat it, and it allows many sites, and these ionic sites allow the charcoal to absorb anything going through it. And GAC treats oil and gasoline dissolved in groundwater, other volatile organics, chlorinated volatile organics. It treats them very well. It also will treat PCBs, pesticides, some metals, lead, mercury. It'll also treat PFAS compounds. So what happens, so either you have a larger vessel that may hold up to a couple of 1,000 pounds of granular activated carbon, to a smaller 55-gallon drum if you're pumping at much lower flow rates. And typically these GAC vessels are put in series or parallel, and you will collect groundwater samples from the influent to the GAC canister, in between two canisters, and to the effluent. And we do this because we want to see how well the GAC is treating the water, but also how long the GAC will last before it has to be changed out, because eventually all these sites get filled up, the GAC gets saturated, and it's got to be replaced. And of course, the GAC itself either needs to be recycled or properly disposed of, because it becomes a hazardous material. So next, two types of air stripping technologies. First, the older type, conventional type, and it's been used for probably 60, 70 years in the drinking water treatment. So, and basically this tower, it can be anywhere. I've seen 10-foot towers, I've seen 50-foot towers. The way it works is you have a tower that's packed with this packed media. This packed media, it can be stainless steel. A lot of times we use Teflon, and it looks kind of like wiffle balls. It's got, or a three-dimensional snowflake maybe. And the reason it looks like that is it's got high surface area, and it allows water to trickle down through it and to break the water from a flow into basically droplets. And the water comes in, it's sprayed onto this media, it trickles down through, and eventually goes to the bottom where it's discharged. Now, the second part of it is you have an air blower assembly, and you have air blowing into this tower countercurrently to the water. So the water's going down, the air is going up, and that air, when it makes contact with the water drops, strips off the volatile organics. And when it strips the volatile organics, they go to the top, and they're actually discharged out of the top of the air stripping tower. And that's the way it used to be, but certainly in the past 40 years, we've collected those vapors and we've sent them to some type of vapor phase treatment, whether it's GAC or, again, catalytic incineration. So that's the old technology. And the problem with this technology was it takes up a lot of space. You can't really put it in a treatment building unless you cut a hole in the ceiling. And even then, so it's very, very labor intensive. Well, there's a better way to do it. And that better way is tray aeration air stripping, or called shallow tray air strippers. And they use the technology around a trickling filter, and they put in a series of these trays. In this case, there are 4 trays. And the water goes in the top. It trickles down through the trays, does the same thing that the high surface area media does. It causes, the trickling causes water to break down into drops. Goes down through these 4 sets of trays. Air is blown in, also countercurrent. So here's the air compressor. It's blowing air up through it. So the air is blowing upward. The water's trickling down. and the volatile organics, again, are stripped. And they're stripped, they're sent to vapor phase treatment, and the treated effluent groundwater is discharged. Now, sometimes we're not getting the treatment efficiency we want, so that's when we would use air stripping in combination with granular activated carbon. So it would go through an air stripping tower first, then it would go through a GAC unit or units before it finally gets discharged or recharged to the groundwater. One type of method to treat the off gas from an air strip or either of the two types of air strippers would be catalytic incineration. And this type of catalytic incineration is also used at landfills. And this will basically, it'll burn and break down the VOCs. It can also break down nitrogen compounds, sulfuric compounds, and you're left with carbon dioxide, water, some nitrogen, and maybe some sulfide or sulfate. This is good for VOCs, SVOCs, PCBs, and also pesticides. So it does a good job of breaking down the large chain compounds. I used to work at Raytheon, and they were one of the Superfund contractors or subcontractor, and I was working, my client was the EPA, so we were working as EPA Superfund oversight contractors. And there was a site up in Maine, and this site had chlorinated solvents that was getting into a stream that was directly upstream from a drinking water well. And the contractor put in a series of monitoring wells and then treated in situ treatment of the groundwater using chemicals. In this case, it was sodium and potassium permanganate, which tends to turn the water purple. And that was used in situ, but then there was also a series of boundary pump and treat wells. So they were extracting groundwater, and then they ran it through both air stripping, but instead of going through granular activated carbon, it went through a ultraviolet oxidation reactor. And the UV oxidation does a really good job treating, breaking down VOCs, CVOCs, fluorinateds. Also things like nitroamines, it'll break down pesticides, and also things like algal toxins, and it will act as a biocide in addition to everything else. Lastly, ozone water purification. And this does a good job for treating, for iron removal and filtration, manganese removal and filtration, and a lot of groundwater for drinking water especially has that as a problem, along with H2S, hydrogen sulfide. It will help deal with water, taste and odor, water disinfection. It will get rid of bacteria, coliform, and total organic carbon. And the way it works is ozone, or O3, is produced when air at high voltage. So when it gets injected into the water, it oxidizes soluble metals, so it turns into an oxide, and filterable particles, and it also kills bacteria. So it goes from ozone injection to aeration, and in aeration, water is pumped into the aerator, forces the ozone and other gases out through a self-cleaning valve, and then that water, which is starting to have oxidized particles, flocks, they get filtered through natural media. This requires only water for backwash and no chemicals. So this is a fully automatic system. This is used more for drinking water treatment, but it's also been used for groundwater remediation of hazardous materials. So back in the 80s, I worked for a company called Groundwater Technology, and I worked up and down the East Coast. I worked all across Canada, and we put in probably 500 or 600 of this type of NAPL recovery system. And if you look at this cross section, you see that it's a cross section of an extraction well, a remediation well. The groundwater pump is in the bottom of the well. And the thing is, when we're dealing with petroleum hydrocarbons, which we were here, these types of pumps had to be retrofitted to make sure there were no exposed wires, that there was no potential for any spark. Everything had to be made into intrinsically safe pumps. So, in addition to the pump, there would be a float switch that if the groundwater was ever drawn down to the point where it got near to the pump intake, it would shut down, because if that groundwater pump pumped air, it would burn it out. So we have the groundwater pump at the bottom. So that's pumping, and that's pumping to either a storage tank and later treatment, or it's pumped and directly treated with air stripping or carbon or GAC. And then a second skimmer pump is placed at the depressed groundwater table. And you see that by groundwater depression, the LNAPL will tend to flow towards the well, and the thickness in the recovery well is greater than the actual thickness in the formation, because you're creating an area of higher permeability. So this second pump is equipped with an oleophilic filter, oil-loving filter, and this pump would pump the LNAPL out of the well to a storage tank. And again, the LNAPL, if it's, for instance, I worked on a job up in Newfoundland at an old U.S. Army Air Force base, the Newfoundland, the airport, and they couldn't use, this was jet fuel A, which is like diesel fuel. They would not put it back in the airplane. They were afraid, and I don't blame them. But they were able to remove the water, any water that mixed with it, and they used it for home heating oil, what they call burner fuel. So they were able to recover some of their loss in the expense of putting in the system with selling the burner fuel. Now, LNAPL, the technology is pretty straightforward, and it's been used extensively all over the world, really. But when we start dealing with DNAPL, dense non-aqueous phase fluid, we've got a much more difficult problem. The problem is that being dense, if there's enough of it, it will tend to sink, go right through groundwater and sink to the bottom of the aquifer. In addition to that, these chlorinated solvents tend to get bound up in residual saturation. So they get bound up and they replace the water from coating the soil grains, and they coat the soil grains, and they get stuck there, and they're really hard to get rid of by pumping and treating. One method you can use, and you see here that here's the release. The release moves down. It hits these 3 or 4 clay layers. And then it comes off of the clay layer, keeps going down. It goes right through the groundwater. It hits the top of the bedrock surface. Now, if the bedrock had no fractures in it and was impermeable, well, then you get a pool of DNAPL building up at the base of the bedrock. Or if you had a clay layer, it would do the same thing. Unfortunately, most of the time, if it's clay, the DNAPL will tend to break up the clay particles, and it'll go through clay. Or if there are fractures in bedrock, it'll get into the fractures, and it'll be very difficult to recover it. And the thing about these chlorinated solvents, they are soluble in water, but very, very slow to solubilize. So you could have a pool of DNAPL if you couldn't find it. That would solubilize. It could solubilize over a couple of 100 years. So it's difficult. It's been found that either air sparging or soil vapor extraction has been a more effective method than groundwater pump and treat. But if you do find a DNAPL pool at the bottom of an aquifer, you can flip the dual phase recovery and put in the DNAPL skimmer pump at the bottom of the well, and then put the water pump at a higher level and pump it. Also, you're creating a cone of depression, so it will draw the NAPL towards the well. That is more difficult. It's a lot more complicated, and it's shown to be not quite as effective. Reactive walls. So my experience with reactive walls. I worked on a project for a town in eastern Massachusetts. My company, we actually, it was a competitive bid. We bid on it, but the bid was a bid for qualifications as opposed to costs. So and this was back in the 90s. So we were able to get the contract, and the issue was there was a school in this town, and the school was at the bottom of a hill. On the top of the hill was a electronics manufacturing firm, and they use chlorinated solvents. They use PCE and TCE. They also had poor housekeeping, and a fair amount of PCE and TCE migrated into the groundwater, contaminated the groundwater, and flowed off of the hill down underneath the school building. We were brought in because teachers and students in the school building were complaining about headaches and getting sick. So the thought was that, well, the chlorinated solvents, as dissolved chlorinated solvents, as they flowed underneath the building, they volatilized, they got into the school, and the teachers and students were breathing it in, and they got sick. So we were brought in with a few other contractors, and we put in a subslab vapor extraction system. So basically, as the vapors were coming up through the floor of the school before they got there, this extraction system would draw a vacuum and grab all of the chlorinated VOCs, the vapors, and treat them and discharge them. Treat them and discharge the clean air to the atmosphere. And they were treated with granular activated carbon. So, great, problem solved. Well, not really. We found out after we went through this that one of the problems was that there were high carbon dioxide concentrations in the school. And more likely, this is what was getting the teachers and the students sick. It was higher carbon dioxide concentrations. Well, come to find out that the custodians, to save money on heat, blocked all the fresh air intakes. So that really was the problem. So, but there was still that contaminant plume of dissolved chlorinateds flowing. And as it flowed under the school, it flowed towards a large aquifer. At the other, about 2 miles down, there was a well field for a local town, and that's where they got all the drinking water. So how to stop it before it contaminated these drinking water wells? And that's where the thought was to put in a permeable reactive barrier. And this reactive wall, basically you're digging a trench across, and the trench has to be perpendicular to groundwater flow. It's got to be wider than the contaminant plume, and it's got to be permeable. So groundwater, contaminated groundwater, it'll continue to flow through it. So you dig a trench down to the base of the aquifer, either bedrock or to, let's say, an impermeable clay layer. And then you fill that with a permeable media. In this case, iron filings were used. And iron filings will tend to absorb and filter out volatile organics. You can also use granular activated carbon. This works well with VOCs, with pesticides, and with metals. If you're dealing purely with metals, in other cases, they've used limestone and shell fragments. The calcium carbonate will, the calcium will be pulled up, the metal will be pulled in, or mulch. Mulch works well because the organics in the mulch will tend to draw VOCs and also metals out of the groundwater. So here's the source. You've got the plume, dissolved plume going in the direction of groundwater flow. It encounters this permeable reactive barrier. The reactive barrier grabs all of the contaminants out of it, and then it flows through to the other side, and you have basically drinking water quality groundwater. It's a really good method. It is an extremely expensive method. We're talking multi-million dollars to install one of these systems. But the town whose drinking water supply was imperiled, they had no other source of drinking water. They used the reactive wall. It was the best thing. And besides, they went back after the cause of it, the electronics company that caused the contamination in the first place. So, soil vapor extraction. Now, normally you think of soil vapor extraction as extracting VOCs and chlorinated VOCs from the unsaturated zone in an aquifer. Well, the beauty of soil vapor extraction is it creates a negative pressure, and if it's a high enough negative pressure, it will actually volatilize these compounds out of the groundwater. So this can be used both as a soil and as a groundwater remediation method. And you have a vacuum creating the negative pressure. So this soil vapor gets drawn into this vapor extraction well and gets drawn out of the aquifer, goes up, it'll go through some type of vapor phase treatment system. Usually it's granular activated carbon, and then it may go through a secondary catalytic incinerator. And it tends to work very well. Overall, it is less expensive than doing groundwater pump and treat because the capital costs of putting in multiple small diameter soil vapor extraction wells is a lot less than putting in a 6 or 12-inch diameter pumping well. And you're not dealing with all of that groundwater to treat above ground. You're vaporizing all of those contaminants in situ. It gets into the vadose zone, into the unsaturated zone, or it gets taken in by the SVE extraction wells and treated above ground. It is more cost effective. Well, to kind of speed up the process, there are a couple of other methods, air sparging and bioslurping. So air sparging, this is a technique that involves the injection of pressurized air. So you're putting in an injection well below the water table, but instead of injecting water, you're injecting air. And this air will bubble up, and the air will, in the below groundwater, it will tend to draw the volatiles out of the water into the air. It bubbles up, gets into the unsaturated zone, where you have a series of soil vapor extraction wells to take it out. You can do that in combination with groundwater pump and treat. So the extracted air and the off gases are treated to remove any toxic contaminants. So again, this is cheaper and more effective than groundwater pump and treat. So the bioslurping part of it, well, bioslurping combines the elements of both bioventing, which we'll talk about, and vacuum enhanced pumping of free product to recover free product from groundwater and soil. And it also, added benefit, it bioremediates soils. So the slurper uses a slurp tube, which basically gets extended into a layer of L-napple, and it relies on capillary action to remove the L-napple from the water. Another method is bioremediation, and it was funny, when we first started doing bioremediation, this is like 30 years ago, people were thinking, well, wait a minute, you're going to put all of these bugs, this bacteria into the ground. It's going to contaminate the ground with bacteria. Well, for the most part, I would say probably 90% of all bioremediation uses the natural bacteria and fungi and other microorganisms. A lot of them already have the capacity to metabolize contaminants. Some are aerobic, some are anaerobic. In situ bioremediation is the process of decontaminating polluted sites by using native, and sometimes we do have to use external bioorganisms. In this case that you see here, we use the natural organisms. We injected nutrients, a lactate substrate, and I guess in this case, because ethyl dibromide is difficult to degrade, we injected a particular type of bacteria that likes to eat that type. But generally, for the most part, especially when you're dealing with gasoline and fuel oil, you don't have to do any of that. The only you may want to put in, you may want to pump oxygen or put in oxygen releasing chemicals to increase the amount of oxygen to and with a nutrient or a series of nutrients to enable the aerobic bacteria to thrive. And after they've eaten the nutrients that you inject, well, maybe they, some of them will turn to gasoline or fuel oil, and they'll start munching them. And the beauty of bioremediation is it takes a contaminant, it takes a natural organism that consumes it, and the waste that comes out tends to be carbon dioxide, could be oxygen, some oxygen, actually carbon dioxide and water. With anaerobic bacteria, well, it will anaerobic bacteria does a pretty good job metabolizing chlorinated solvents, which aerobic bacteria pretty much the chlorinateds are toxic to. So the anaerobic bacteria will dechlorinate the chlorinated solvents and break them down from a complex, more complex chlorinated solvent like tetrachloroethylene. Tetra has 5 chlorines, I mean 4 chlorines, to trichloroethylene with 3, dichloroethylene 2, excuse me, chloroethylene 1 to vinyl chloride. Most of the time, the when biodegradation, bioremediation goes on, it will take a toxic substance to make it less toxic. In dealing with chlorinated solvents, the one problem is when it breaks it down to vinyl chloride is actually a known carcinogen. You can't smell it, taste it, see it. You breathe in, you're not breathing in. It is a carcinogenic compound, so that creates some difficulties. Bioventing, similar to air sparging, except instead of adding like an oxygen releasing chemical, you're actually pumping air. And it's similar to air sparging, but you're pumping air into the subsurface, both above and below the water table, to increase the amount of oxygen, especially below the water table. You're increasing the amount of dissolved oxygen. And this enhances the growth of these contaminant-consuming microorganisms. And here's an example how to do it. They've got a vertical vent array. They're pumping air down. And in this case, which is very close to the source, they also put in a lateral vent array. So you can use horizontal or vertical wells to inject the air into the ground. So there are some enhanced bioremediation methods. So an enhanced way of breaking down hydrocarbons. So here's a cross section. This was courtesy of the CLUIN program at the US EPA. So we have a spill site, and we have a series of wells. So we've defined the spill site. And here's the contaminant plume. Here's the direction of groundwater flow. So you have an anaerobic reduction zone. So the bioremediation is going through a series of anaerobic processes. And so you're going to get anaerobic bacteria that's breaking down the compounds in this area. So you're taking carbon dioxide, you're adding hydrogen, you're breaking it down to methane. The next zone, it's a sulfate reduction, iron reduction, manganese reduction, then a nitrate reduction. And then it goes, as the concentrations decrease, you go from anaerobic to aerobic. And then you get aerobic respiration, and you're dealing with aerobic bacteria as opposed to anaerobic. So you're getting aerobic bacteria. Breaking down what's left of the contaminant with aerobic respiration. So that is groundwater remediation methods. And there are other methods that I haven't talked about, but these are kind of the primary ones that I have learned about and that I've actually done myself. So then we get to slow remediation methods. And, you know, we're going to go from old school to some higher tech ways of remediating. And there's a couple others I will talk about that aren't in the slides that I haven't used, but they're out there. I will briefly discuss them. So